So physical chemistry, 364. By the end of the semester, I will memorize these numbers. And there are several skills replacing mathematical derivations that will help all of us to progress to the successful end of the course. And the skills include some minimalistic level of scientific programming with matter. Last time, class activities presented these background skills. Now we are applying them to propagating of the wave packet, propagating of the wave function in space and time. So all presentations are arranged to serve this task. There are potentially 8 presenters, 7 are confirmed for sure. The Adam may or may not join. And the plan is to have 4 minutes for presenting and 1 minute for questions. I am very happy for longer talks, but please be responsible because some of us need to attend a class at noon. Otherwise, we could do this session for 3 hours because it is a whole subject. So if you are online, you can just share screen and enable camera.
Okay, so I had principles of wave packet propagation in momentum operator, Hamiltonian, and evolution operator. Okay. So when you're doing wave packet propagation, you start from your current wave function, psi of x and t, and you want to get it to a wave function that will be in the future. So psi of x and t plus delta t. And to do that, you'd multiply the initial wave function by the evolution operator, which is e to the negative I over h bar times a Hamiltonian times delta t. And then the evolution operator is dependent on the Hamiltonian. The Hamiltonian is the momentum operator squared. And I apologize, this isn't a p hat. They didn't have that in the symbols when making the slides. So the Hamiltonian is the momentum operator squared over 2m plus the potential. And then since the Hamiltonian is dependent on the momentum operator, we need to know the momentum operator, which is negative I h bar, the partial derivative, negative I h bar with a partial derivative with respect to x, and then that'll be for finite differences. So for momentum operator, we have the momentum operator times the wave function of x, and so you'd have negative I h bar times a partial derivative with respect to x of the wave function of x, and then that would work out to negative I times h bar times psi of x plus delta x minus psi of just x. And then when you would do this in matrices, so you'd have it in vector form. So to do this, so you'd initially do row times column, so it'd be -1 times psi of 0, and then it'd be 1 times psi of delta x, which would work out to psi of delta x minus psi of 0, multiplied by negative I to the h times h bar, and then that would equal the momentum operator times the wave function. And then it would just keep progressing, shifting right one. And I also apologize for the matrix. I couldn't get it to work out cleanly on PowerPoint. And then as far as the code goes, so in line 5, you have P naught, which is initially set to 0.25, and that's the initial momentum in atomic units. When I didn't have the animated plot, but initially they all start at a peak of 30 at x is 30, which makes sense, the initial position. And then what we can see here is that the graph for the 20 atomical units has a much smaller shift from 30 compared to the initial momentum of 45 atomic units, which makes sense. In the higher your momentum, the more you're going to travel, which we can see in these graphs. And then, when solving for this, once we solve for the momentum operator, we just plug it into the Hamiltonian and solve for the Hamiltonian, and then we can plug in the Hamiltonian to the evolution operator, and then we can solve for the wave function in the future. And then that is it. That is it.
Okay, please join me in thanking Connor. Any questions in or online? Will you please put slide number 3 on the screen? The previous one, not 4, but 3.
Oh, my bad.
Okay, anyone in the class or online wants to ask a little picky question? It's not like most fundamental, but just it looks like a typo or one factor is missed.
I think it's the parentheses around psi x plus delta x minus psi x.
Thank you, August. And anything else?
No.
In the first time after equal sign, you have I h bar ddx, right? And second time you have differences of psi x plus delta x minus psi of x. Where is your dx? One should just divide by dx. And if one will do it numerically, if one takes large dx, then momentum will be small. If one takes it huge, dividing by big number, it's like depending on dx, momentum is changing. And we set up dx as a constant that defines how things are going. Okay, great talk. More questions 1, more questions 2, more questions 3. Let's thank Connor once again. What is yours?
Okay, thank you so much. All right, so today I'm going to be talking about electron quantum dynamics through like numerical methods. Essentially, this presentation is just going to be on the types of methods that we would use for, numerically solving these quantum dynamics, as well as these sort of fundamentals of what exactly we're doing in these methods. So first, we're going to start with just like the simulation methods, as well as like some of the precursors to what exactly we're doing to simulate this sort of wave propagation that's shown in a lot of the code that we've been using recently. So first, we're going to start out with Gaussian wave functions. It's basically just a certain type of wave function that takes the form of a times the exponential of negative x minus b squared over 2c squared. Now, the technical, more rigorous formulation of this has a lot to do with statistics, but this is just a more general form of that expression. This describes a probability distribution function with a normal distribution. What that basically means is that we're assuming that a certain variable, let's say, x, or we could say the momentum, has some sort of normal distribution across all of space. And this is what the function takes the form of. It describes the ground state of a harmonic oscillator, which is somewhat rigorous for what we're looking at, because we're assuming that, it's going to be a harmonic oscillator. So that's basically the basic assumption. As for operators, we have the evolution operator, which is used to evolve the wave function based off of the wave function's past, and seeing where it will go based off whatever time step you're using, as well as the action. We also have the Hamiltonian operator and the momentum operator. And these are just basic definitions that we need to show. As for Fourier transforms, basically what it's doing is we're providing frequency decompositions in whatever type of phase space we're using. So let's say we're using regular momentum space. We would have these two relations. As for Gaussian wave functions, if we plug them into those Fourier transforms, we're going to get Gaussian wave functions back. So if we have a Gaussian wave function for the position wave function, we're also going to have a Gaussian wave function for the momentum wave function. It's useful for showing basically how phase space dependent wave functions operate in each variable of phase space. This is just showing the Heisenberg uncertainty principle in a way, because you're going to have an uncertainty of momentum and position. Now let's talk about the first method, propagation in momentum space. So this is describing a Gaussian-based momentum distribution where the wave function propagates in momentum space. The first step is to define an initial wave function, then to Fourier transform that wave function into momentum space, numerically simulate that propagation using the evolution operator, then to inverse Fourier transform those iterations back into position space. And if we're looking at that sort of method one, we first have our initial function. So our initial wave function is the psi naught equals square root dx, yada, yada, yada. And then we set up our time steps. So we have all values of positions and all values of momentum. And then we can do our fast Fourier transform on psi naught. Then we can use the evolution operator to sort of evolve this sort of Fourier transformed version of psi naught to get the evolved version of the momentum wave function, and then we just keep looping that interaction so then we can show the exact sort of interactions that we're getting. All right, now on to method two, where we're doing propagation in position space. This describes a Gaussian-based wave function distribution where the wave function is propagating in position space. So we define the initial wave function as Gaussian wave function. You can define it as whatever you would like, but in this case, it's going to be Gaussian. We Fourier transform the momentum operator into position space, then use the Fourier transform momentum operator and the Hamiltonian and evolution operators, then numerically simulate the propagation using the evolution operator, which is very similar to method one. As you can see here, we have our momentum, and we have our position defined as operators. Then we use those operators to Fourier transform them into position space. And once we Fourier transform them, we can put them into the Hamiltonian as well as our evolution operator. Then we can loop that evolution operator. And once it's all looped, we get a simulation of how that wave packet would change. So for method three, we have discrete matrix derivatives used in evolution operators. So what this is basically we're going to be using a Toeplitz matrix to define a derivative as a finite difference, essentially. So this is going to be a finite difference, and we're going to use this to sort of change the wave function. This is going to be describing a Gaussian-based position distribution wave function. This is going to be basically the same as method two, where the wave function propagates in position space. First, we're going to define an initial wave function as a Gaussian wave function, discretely define the derivative as a matrix, basically a Toeplitz matrix, and then it's going to act on our wave function, and then we're going to use that in the momentum operator. So using this newly defined momentum operator, we can plug that into the Hamiltonian and the evolution operators and numerically simulate the propagation using the evolution operator by using a for loop. So in this case, we have our initial function. Then we are defining that Toeplitz matrix that defines sort of what our momentum operator is going to be. Once we have our momentum operator defined in finite differences, we can apply them to the Hamiltonian and our evolution operator, and then our output is spit out when we do the for loop, which is just going to be looping that evolution operator. All right.
Okay, with joining thinking August. Any questions from the class? From in physical presence? Any questions from online? I do have one.
Yep.
So, what are the restrictions for the method number 1?
The restrictions for method number 1. So let's go back to method number 1. Well, I would say the restrictions would likely lie in the Fourier transform. So the Fourier transform, the problem with it is that it's a very lengthy operation and can often take a lot of time, or either that or it's just not very well suitable for integration. So we're going to be using a fast Fourier transform like shown in here. So that's going to be our main sort of bottleneck. And fast Fourier transforms can sometimes provide some issues. So that's from what I can see at least.
Yeah, thank you. You are going in the right direction, but we need to collectively analyze this question. So please keep this slide on air. I am going to attract your attention to the left side,
okay.
Third box that before that tells E tau. Can you mark or just circle your cursor around it?
Okay.
Yes, yes, the E tau box above.
Yeah.
Okay, so which components of Hamiltonian are added into this evolution operator?
How, I think. No, wait, no.
It is not a tricky question. It may be shocking in its verbalization, but it's very, very basic. So if you and previous speakers defined that evolution operator should have imaginary exponential into the power of Hamiltonian, right? So what is playing the role of Hamiltonian in this E tau? And I believe Zane is also able to hear him.
H bar hat.
So is it potential or kinetic energy?
It's going to be, I would say, kinetic.
Correct. Is there a potential energy in this definition?
We haven't defined any, so I would assume not.
So in the form as it is defined right now, it will work only if potential equals 0.
Yep.
This method 1 will be uniquely applied only to particle in a free space. As soon as one goes into potential that describes something realistic, one needs either to forget about number method 1 or to update this line with E tau.
Yep.
While other methods already integrate potential. Why it is skipped and not pushed forward? Because in order to convert potential into momentum space, one needs to practice double Fourier transform. And then it loses any way of being visually appealing for humans.
Yeah.
Okay, more questions to August? If no, please join me thanking him once again. It's yours.
Awesome. Well, we're doing the commutation of operators and conversion between momentum and position, and then in the end, find out how we're going to upload it to YouTube, which was a struggle. So the commutation just represents that A comma B in square brackets is equal to AB minus BA. And if it's equal to 0, then AB is commutable. But if we look at our positioning momentum operators, it equals I H bar, and this is the matrix with 1s down the diagonal and 0s everywhere else. So forget the name of it. But if we move the square brackets to these pointed brackets, we can say that equals 1, which would give us the equation of this. which is called the canonical commutation relationship. And now the conversion of operators between momentum and position. In this top corner, or right here, it's just the integral between -infinity and infinity of our wave and our EI position momentum over h bar. We can turn that into a double integral, and we can see that we now have two different equations that is changing the, in this case, the momentum into the position operators, and A of P comma P or X comma.
I just want to remove this. Whoever online doesn't see it, but here we have this black box blocking. Okay, please continue.
It's just the matrix with a momentum operator or the position operator. And all this matrix is negative delta momentum operator, zeros everywhere else, and momentum operator. Then in the code, we can see up here, the position operator is h bar over k, but it's still a vector. So we have to, down here, px, we can see it's w prime times position operator, or momentum operator, times w over n points, which converts it into a matrix. And that equation is relative to this equation right here in code. And then all of these are variables that we can change. And this will give us different graphs and wave packets within the code. And this is just some graphs on the code. So if we do the mesh of the position operator, we can see it's negative, but goes into a positive numbers. And the matrix for this would just be negative down here, positive up here, and a diagonal. And then for our x operator, we can see that the graph just goes straight up. And this is, you can look at this as a matrix as well, with zeros everywhere where it's flat, and only in this line we have numbers that aren't zero. And if we mesh these two together, we can see that we're starting to form this parabola here, with our negative numbers here and our positive numbers here. This is the mesh of imaginary px. So we can see a wave forming here with positive on each side and positive in the middle, where we can see the wave starting to form. And then this is the mesh of the this might be real and this is actually imaginary, where we can see, if we zoom in here, we have a bunch of little waves with a gap in zero, which correlates to this graph where there's no waves here, one big wave here, waves out there. In this graph, we're meshing the commutation operator with x op, or position operator, momentum operator, minus the momentum operator times position operator, which we see as zero, which means these two can commutate after we plug in the equation in the code. These are also just different graphs with I was just messing around seeing what would happen. We can see that this is a 3D graph, two triangles coming into the middle and out. And these are the real values, and these are the imaginary values. And you can see if you line the two graphs up on top of each other, they correlate pretty well, with the larger numbers to the outside and no numbers in the middle. Now this is where I had some real trouble with the code, since we had to add a few lines of code to get the code that we got able to run as a .avi. And the code I added was the video object, opening the video object, and then closing the video object with current frame. Then once we have that, it'll save in this .avi, or in this AVI file as a .mp4. We go to YouTube, hit create, select file, click on your wave packet, then you will get this video right here. And it's just the moving part of the code that we ran. And thing. And thing. And thing. That's it. And
Okay.
These are the references that I use.
Please join me in thanking Zane for interesting and important presentation, and questions from here or from online are very welcome. Brief one. It looks like the computation relations that you declare at the beginning is not always fulfilled, right?
Correct.
We agree that if one uses the third method with px3 and x operator, then it is as close as possible to the
Clear. Yeah.
expected. Okay. And August, when presenting next, may comment on the third method. More questions to Zane? If, of course,
I don't have any questions.
Okay, let's thank Zane once again.
So I'm talking about the wave function representation, normalization, and simulation. So first, we can represent the wave functions using some various graphs. On the left here is the code that we can modify, determining, so we can change the number of like num points, the initial position, the initial momentum. That's small. So you can change like the initial momentum, the initial position, change the graphs that we can see. And this MATLAB gives us, I believe this is called figure 4, when we run the code. And so we get the time versus position, and it gives 3 graphs, one in the 3D model, a linear model, and an exponential model. So next I'll talk about the normalization of wave functions in discrete representation. So in the code, it's line 66, which you can see on the screen here. And unlike the normal normalization found here, where we take the integral of the wave functions, we're going to use the summation notation, e to the I, or summation of I, of psi I and psi I. And for psi I, we're going to use psi of x, and then the square root of the change of x. So we're going to be looking at the derivative of x still. And then the size versus the time simulation, where T naught is initial momentum, there is a condition with the size of the box and velocity, where the velocity multiplied by the simulated time should be smaller than the box. So the simulation time is n tau times tau, found in line 8 and 9. And then the size of the box would be number points, which is line 3 times the derivative. And then the P naught times the simulation time should be smaller than the num points times the derivative. And here are just some different graphs. So here I changed the P naught, the initial momentum, to 2.5, so quite a bit greater. And then you can see we do not end up getting a linear graph. We get a couple, 2 spots on the 3D graph, and then a Gaussian type shape on the exponential.
Let's thank Jared. And, the question is, can you explain what is periodic boundary conditions? You basically did it, just it's different verbalization.
Periodic
Boundary conditions. What is boundary and what is periodic?
So you have a certain amount of time within.
Like your blue square with stripes illustrates it very well. You can just point on the screen and explain.
You can't be in two spots at the same time. You're only supposed to be at one spot in a certain time, right?
So can you point with your finger or with mouse where the yellow thing? Maybe for online visitors, mouse is better. So where the yellow is mostly yellowish. Okay, right, it is start. Yep. As time goes by, it moves from left to the right in position, right? Yeah. What happens after? After it reaches the boundary, the edge.
Boundary, it would then go to here.
So it after it reaches like 85, it reappears at 0.
Yes.
So it looks like there is a infinite number of replicas of simulation cell that repeats again and again periodically. Therefore, we are able to describe this boundary conditions coming through the boundary. It reappears from other side, but it is just different verbalization for the stuff you already explained. Any questions from class or from online? Please verbalize questions because in a rush we cannot read. Questions 1, questions 2, questions 3. Let's please join me. Thank you, Jared.
Can you hear me?
Yes.
Okay. Okay, so I had accumulation of expectation values into arrays and saving numerical data into files for separate analysis. Sorry, 1 second. Okay, so accumulation of expectation values. So when finding the position of the accumulation of expectation values, you use the sum of the probability. And this was found on line 208 in the code. And so it was average 3 equals sum and then x times the probability 3. And all this line is doing is multiplying the probability by the number of x values. And so for momentum, this can be found on line 232 for the expectation value. And this is AP3 equals PSI3 apostrophe times PX3 times PSI3 divided by norm 3. And so the AP3 is just the average, the PSI3 is the wave function, and the PX3 is momentum, and the norm 3 is normalization. And so the value of AP3 is only used one time, and then when you run the code again, a new value will override the previous value. So then we need to accumulate all of that data. So how we accumulate that data is on line 235, which is AVE P3 equals AVE P3 AP3. And so this is what is accumulating the values of AP3 along the trajectory. And each time that you pass through the loop, the length of this AVE P3 gets bigger every time. And then you can use the plot function to get the value. So then you plot AVGS, and then you get a graph. But for some reason, my MATLAB was not cooperating with me, so I was not able to get any graphs to show you on this. But usually you'd get a graph. And then to save the numerical data in separate files, in the command window, you type save and then a dash, ASCII, and then the file name, and then the same file name after that. So like my example is averages and averages. And this can be uppercase or lowercase, the ASCII. And then you just go into your files and your downloads, and then you open the file in your notepad, and then all of your accumulated data will be in there.
It should be visualization of wave function in MATLAB. Visualization, it is more general and it is not related to the force, but other than that, everything is great. And Spencer?
Yep.
Oh, okay. Yeah, now I do see your camera. It was just coming in and out. Okay, floor is yours. Please go ahead.
All right, so we had visualization of wave functions in MATLAB, and so the contents of what we are going to be covering is visualizing the real and imaginary parts of a wave function, or a wave packet, I should say, visualizing the potential and probability distribution, and diving more deeper into why there are 3 of them. And we're also going to be visualizing any observable and organizing data and bundling groups of observables, so that way it makes it easier for us to analyze. So our first thing right here is I have a cautionary note right here, and it's just that you need to ensure that that you have the code set up correctly. And so if you have your function here, and this is just given from the given code. So if you have plot psi2, this is what you're going to end up getting, and that is not what we're looking for, because that's really hard to interpret. So that was one of my personal failures when I was looking at it. Instead, your modified code from the modified MATLAB should have all 3 of these parts: the x, the real, the imaginary, and then the square root. So this is showing the real and imaginary parts of the MATLAB simulation. The blue is the real part, the orange is the imaginary part. As you can see here, they are oscillating it differently. We have one that's sine, we have one that is cosine, which is known. And the yellow anvil equation at the top just is there to allow for easier calculations, so we can see kind of what kind of general trend is this graph taking. Moving on to potential and probability distribution, and more so looking at why there are 3 of them, because there are 3 different ways to calculate probability and potential distribution, and each of those methods are listed in the code provided, and then you can even put them on the same graph as such right here. So you have one as the dashed line, one as the blue line, and then you have one as the red line as well. Moving on to bundling groups of observables or organizing data. So for visualizing any observable, we've done this in most of the labs, but you're just going to look for the average of your observable and then plot it using the plot function. For organizing your data, the function subplot is going to be the key function to use here. This makes a multi-panel figure in MATLAB, and I'll show that as well as the code to make it on the next slide. Then as for bundling groups of observables, we do this because it's easier to observe and look for patterns, and even it's easier to analyze the graph as well. So if you look at the plot again below, this is the code for it. And so we have x probability 2, x probability 3, and then xv. So here is our multi-panel function. As you can see here, it is subplot. So that gives us the multi-panel figures, subplot 1, subplot 2, and then we have subplot 3. And so these are also, all 3 of these are movable within MATLAB using the MATLAB functions. And so that way you can move this 3D one as you need. And that is the end.
Okay, please join me in thanking Spencer. Any questions face to face? Any questions online? I do have questions as well, because it's really useful and correct. Do you have any question to yourself?
I don't think so.
Okay, then please join me in thanking Spencer once again. Details.
All right, so my presentation's on the applications of the wave packet code. So for the first thing I was working on was making a 1D box that had like a finite energy limit on it. So we can see down here I have that the U2 is the height of the energy. So in the code that's at line 54 here. And I put that at -8. So that creates us a little well here. And if we play this, you can see as the wave packet moves, it'll start to get disrupted, and then some of the energy here will actually start to break through the well, and it won't get trapped in the well or the box. But this portion here does get trapped in the box. And then moving on to a 1D box that is infinite. So in theory, this should just go all the way down, but I put it to -1000, and
that's good enough for me. So that's what this looks like. So we see really it makes no progress at all through the box, so absolutely nothing is getting through. And then the next thing we have is barriers. So for this, I just changed the U2 value. Instead of being -8, I just changed it to 8. So then, well, really it just flipped around. And then we can see again, just a little bit of energy actually does escape down there. But if we remember from before, it wasn't as much. It wasn't nearly as much as we had before with the box, which I thought was interesting. And then next we have a harmonic oscillator. So here we took out the V equals VO times the barrier 2 we have here. And I opened up this command here to actually create our parabola boundary. So then we should see the peak here for the wave packet actually start oscillating. So we see that moving back and forth there. And that's all just because it's kept in the boundary of the parabola. And I believe that is it.
Okay, please join me in thanking team. Any questions? Please come a couple of slides back to the finite.
Finite?
Yeah, here. So
yeah.
Each situation does on experiment does it describe when electron is being captured by a molecule? How do you call it?
Sorry, what was that? Can you repeat the question?
Electron is when you run dynamics, electron is being captured by this potential, which means molecule catches electron. Between two, oxidation and reduction, which one would better come? Would be the better explanation?
What were the two things you said? I'm sorry, I didn't hear you.
Oxidation or reduction?
I believe reduction.
Yes. So you are doing reduction, and you could also try to start it inside, and then check whether it will leave, whether it will be oxidation.
Oh, starting the wave packet on the inside of the box.
Yes.
Instead of okay.
Yeah, and the research projects will be very much similar to what you already did. But
okay.
More questions to Tim? 1, 2, 3. No more questions. Please join me thanking Tim and all presenters. So everyone gets credit equivalent to successful midterm towards final grade. And let me thank all speakers and all attendees. And with this, the meeting is announced complete.